As our newest, most perceptive eye on the ongoing unfolding of the cosmos, the James Webb Space Telescope is revealing many things that were previously unseeable. From planets that rain sand to distant galaxies, James Webb is filling in a mysterious gap in our knowledge about the first 400 million years after the Big Bang, as well as providing clues to the existence of life forms elsewhere in the universe. However, note that James Webb not only gathered striking infrared images, but also caused a few snags in the fabric of the Big Bang theory, questioning some of the facts we thought were well established.
The Big Bang was an interesting event, but not the first event in the totality of reality.
A recent shocking discovery made by James Webb has got the science community abuzz, as it not only could challenge the current standard model of our universe's evolution, but also break one of the fundamental laws of physics.
The possibility that the Big Bang may be incorrect, and that the universe might be larger and older than we think.
What is this discovery, and why does that get cosmologists worked up so much? Join us as we dig deep into how James Webb just shattered our cosmology into pieces. Looking out at our universe today, we not only see a huge variety of stars and galaxies both nearby and far away, we also see a curious relationship. The farther away a distant galaxy is, the faster it appears to move away from use. This continues as far as we've ever looked, and remains true on average for all galaxies. The farther away they are, the greater their observed redshift corresponding to recession is. In cosmic terms, the universe is expanding, with all the galaxies and clusters of galaxies getting more distant from one another over time. In the past, therefore, the universe was hotter, denser, and everything in it was closer together. Imagine what this means if the universe is, and has always been, expanding. Not just for the future, but for our cosmic past as well. If we extrapolate back as far as possible, we'd come to a time before the first galaxies formed, before the first stars ignited, before neutral atoms, or atomic nuclei, or even stable matter could exist. The earliest moment at which we can describe our universe as hot, dense, and uniformly full of stuff is known as the Big Bang. Here's the story of how it first began. Some of you are going to read that last sentence and be confused. You might ask, isn't the Big Bang the birth of time and space? And this is a view that many modern cosmologists can be sympathetic to, as at one point in the history of cosmology, that's how the Big Bang was originally conceived. Take something that's expanding and of a certain size and age today, and you can go back to a time where it was arbitrarily small and dense. When you get down to a single point, where all the matter and energy in the universe comes together at once, that event corresponds to what we know as a singularity, a point from which space and time originally emerge. But we know that's not correct today, in 2023. In fact, there's a ton of evidence that points to a non-singular origin to our universe. We never achieved those arbitrarily high temperatures. There's a cutoff. Instead, our universe is best described by an inflationary period that occurred prior to the Big Bang, and the Big Bang is the aftermath of what occurred at the end of inflation. Let's walk through what that looked like. During inflation, the universe was completely empty. There were no particles, no matter, no photons, just empty space itself. That empty space had a huge amount of energy in it at every location, with the exact amount of energy slightly fluctuating over time, by about 1 part in 30,000, on average. As the universe inflates, expanding in a rapid, relentless fashion, those fluctuations get stretched to larger scales, while new, small-scale fluctuations are created atop them. This superposition of fluctuations of small scales atop intermediate scales, atop large scales, atop superhorizon scales is one of the defining predictive features of cosmic inflation. This continues as long as inflation goes on. But inflation will come to an end randomly, and not in all locations at once. In fact, if you lived in an inflating universe, you'd likely experience a nearby region where inflation came to an end, while the space between you and it expanded exponentially. For a brief instant, you might even be able to detect what happens at the start of a Big Bang before that region disappeared entirely from view. In an initially relatively small region, perhaps no bigger than a human-sized hamster ball, but perhaps much larger, the energy inherent to space gets converted into matter and radiation. The conversion process is relatively fast, taking approximately 10 to the power of negative 33 seconds or so, a brief amount of time, but nonetheless, one that is not instantaneous. As the energy bound up in space itself gets converted into particles, antiparticles, photons, and more, the temperature starts to rapidly rise, from just a few degrees above absolute zero to perhaps cos 10 to the power of 20 kelvins or so over that same brief time interval. Because the amount of energy that gets converted is so large, everything will be moving close to the speed of light. All quanta will behave as radiation with so much kinetic energy inherent to them, regardless of whether the particles are massless or massive. It doesn't matter under these conditions. This conversion process is known as reheating and signifies when inflation comes to an end and the stage known as the hot Big Bang begins. In terms of the expansion speed, you'll witness a tremendous change from all prior behavior when the hot Big Bang first commences. In an inflationary universe, space expands exponentially, with more distant regions accelerating away relentlessly as time goes on. But when inflation ends, the universe reheats, and the hot Big Bang starts. More distant regions will now recede from you more and more slowly as time goes on. From an outside perspective, the part of the universe where inflation ends sees the expansion rate there drop, while the inflating regions surrounding it see no such drop. Under inflation, the distance to any object would double after a certain amount of time, and once that same amount of time elapses, that distance doubles yet again, and again, and again. The process is relentless, but once the Big Bang begins, all of that changes as the expanding universe immediately slows down once the first moment of expansion elapses. Probability-wise, it's extremely likely that from the perspective of whatever region of inflating space you're in prior to the Big Bang, you'll experience inflation ending in nearby regions many times. These locations where inflation ends will quickly fill with matter, antimatter, and radiation, and expand more slowly than the still inflating regions do, leaving you in the inflating region as a typical region within space-time, dominating its volume. These regions, where hot Big Bangs occur, will expand away from all the other locations, where inflation still goes on exponentially, meaning they will very quickly recede from one another's view. In the standard inflationary picture, because of this expansion rate change, there's virtually no chance that any two universes, where separate hot Big Bangs occur, will ever collide or interact. Finally, the region where we will come to live gets cosmically lucky, and inflation comes to an end for us. The energy that was inherent to space itself gets converted to a hot, dense, and almost uniform sea of particles. The only imperfections and the only departures from uniformity correspond to the quantum fluctuations that existed and were stretched across the universe during inflation. The positive energy quantum fluctuations will correspond to initially overdense regions, while the negative energy fluctuations get converted into initially underdense regions. The typical difference might only be at the 0.03% level, but that's still enough to serve as the eventual seeds of cosmic structure. We cannot observe these density fluctuations today as they were when the universe first underwent the hot Big Bang. There are no visual signatures we can access from that early on. The first one we've ever accessed comes from 380,000 years later, after they've undergone countless interactions. Even at that, we can extrapolate back what the initial density fluctuations were and find something extremely consistent with the story of cosmic inflation. The temperature fluctuations that are imprinted on the first picture of the universe, the cosmic microwave background, gives us confirmation of how the Big Bang began. What might someday be observable to us, however, are the gravitational waves left over from the end of inflation and the start of the hot Big Bang. The gravitational waves that inflation generates move at the speed of light in all directions. But unlike the visual signatures, no interactions ever slow them down. They will wash over us, arriving continuously, from all directions, passing through our bodies and our detectors. All we need to do, if we want to understand how our universe got its start, is find a way to observe these waves either directly or indirectly. While many ideas and experiments abound, none have returned a successful detection so far. We know what the spectrum of these fluctuations will look like, and what imprint they'll have on the light within our universe. But we have no idea what their magnitude is. Different models of inflation make different predictions, and only by measuring them can we determine which model accurately describe our universe. Once inflation comes to an end, and all the energy that was inherent to space itself gets converted into particles, antiparticles, photons, etc., all the universe can do is expand and cool. Everything smashes into one another, sometimes creating new particle or antiparticle pairs, sometimes annihilating pairs back into photons or other particles, but always dropping in energy as the universe expands. The universe never reaches infinitely high temperatures or densities, but still attains energies that are perhaps 1 trillion times greater than anything the LHC can ever produce. The tiny seed over densities and under densities will eventually grow into the cosmic web of stars and galaxies that exist today. 13.8 billion years ago, the universe as we know it had its beginning. The rest is our cosmic history. Well, as you see, amidst the boundless panorama of the cosmos, we teeter on the cusp of groundbreaking revelations that promise to revolutionize our perception of the universe. And the arrival of the James Webb Space Telescope expands the reach of our celestial exploration, probing deeper into the mysteries of space and time than ever thought possible. Embarking on this uncharted voyage through Webb's discerning eye, we're offered an intimate look at the enigmatic, early universe, thereby defying conventional astronomical paradigms. As we venture into this enlightening domain, the mosaic of our understanding unfurls, unveiling intricate designs and concealed complexities. Can you imagine peering into a time machine, revealing stories from eons ago? Well, James Webb has done just that. Its first deep-field image, composed of a mosaic of 690 individual frames, portrays a patch of sky in the vicinity of the Big Dipper's handle, approximately 8 times larger than its predecessor. It's like holding a massive interstellar jigsaw puzzle, where each piece is an individual galaxy from the early universe. These images present an intricate ballet of galaxies, some of which existed merely hundreds of millions of years after the Big Bang. Their faint glows, a silent testament to their distance and age, were unveiled by the unparalleled infrared sensitivity of James Webb's near-infrared camera. This marked a monumental leap in cosmic exploration, providing an unprecedented look back into the universe's nascent epochs. In the following discovery, the James Webb Telescope is changing astronomy in many ways, from peering into the atmosphere of exoplanets to capturing stunning images of distant cosmic phenomena. But perhaps its greatest scientific contribution is its ability to observe galaxies that are so distant that looking at them is like looking back in time. Projects like Webb's Cosmic Evolution, Early Release, Science, or CERAS survey are scanning the sky to pick out some of the oldest galaxies we've ever seen. When scientists first turned Webb toward apparently empty patches of sky to look for these distant galaxies, they found something very strange. They didn't just find a few very old galaxies dating back as much to just a few 100 million years after the Big Bang. They found far more of these galaxies than anyone had predicted. These unexpected findings then results in a galactic controversy that has astronomers around the world excited and puzzled. They caused a few snags in the fabric of the Big Bang Theory, questioning some of the facts we thought were well established, such as the timelines of when certain things happened. In an attempt to explain the shockingly bright, highly structured, and possibly quite massive galaxies existing so early in the timeline of the universe, a researcher has posited that the universe is roughly twice as old as previously believed. They push the age of the universe from a spry 13.8 billion years old to roughly 26.7 billion years old. An article published earlier this year in the journal Monthly Notices of the Royal Astronomical Society came to this conclusion after combining two models of the universe. One is the commonly accepted model for the expansion of the universe. This model explains that as the universe expands, the light from galaxies must travel further and therefore shifts from a bluer to a redder spectrum of light. The other model it is combined with has been debunked. It's called the tired light model, and it alleges that as light travels across the universe, it gets redder because it gets tired or loses energy. That combining the models is clever, but it would be best if you were cautious against quickly jumping on this supposition that the universe is twice as old as previously thought. Anyway, extraordinary claims require extraordinary evidence, but no such evidence has been found. In other words, we need more data from the James Webb Space Telescope, and with additional data comes possibilities for new solutions, and it's really worth waiting. While James Webb is revealing secrets from the earliest era of the universe, its data also backs up ideas on planet formation. Where do planets come from? The entire process can get complicated. Planetary embryos sometimes run into obstacles to growth that leave them as asteroids or naked planetary cores. But at least one question about planetary formation has finally been answered: how they get their water. For decades, planetary formation theories kept suggesting that planets receive water from ice-covered fragments of rock that form in the frigid outer reaches of protoplanetary disks, where light and heat from the emerging systems lacks the intensity to melt the ice. As friction from the gas and dust of the disk moves these pebbles inward toward the star, they bring water and other ices to planets after crossing the snow line, where things warm up enough that the ice sublimates and releases huge amounts of water vapor. This was all hypothesized until now. NASA's James Webb Telescope has now observed groundbreaking evidence of these ideas as it imaged 4 young protoplanetary disks. The telescope used its medium-resolution spectrometer of Webb's mid-infrared instrument, or MIRI, to gather this data, because it is especially sensitive to water vapor. Webb found that in 2 of these disks, massive amounts of cold water vapor appeared past the snow line, confirming that ice sublimating from frozen pebbles can indeed deliver water to planets like ours. Webb had its proverbial eye on 4 protoplanetary disks that were only around 2 or 3 million years old and forming around Sun-like stars. Out of these disks, 2 were compact, while the other 2 were larger and had multiple gaps interrupting the disk. The research team behind this investigation wanted to see whether water was brought to the inner disk through the sublimation of ice on pebbles that drifted inward from the edges of a disk. They were also trying to make out whether this happened more efficiently in compact or larger disks. Past studies done with NASA's Spitzer Space Telescope and ALMA had found some data suggesting that pebble drift from the outer to the inner parts of a disk, along with subsequent vaporization of ice, was possible. Unfortunately, the data was unclear because of its low resolution. Spectral lines that identified the presence of water were blurred. Webb's higher resolution was able to separate these lines, so they were much more distinct and showed the spectra of warm and cool water. The Webb researchers were looking for cool water, which would indicate sublimated ice that confirmed previous ideas of frozen pebble drift. Warm water in a disk could only go so far as evidence, as it would probably mean that drift and sublimation had already happened, and the water vapor that resulted had now been heated by the nascent planetary system's star. In the two larger disks, it was found that frozen pebbles in larger systems have a hard time getting through the gaps. They are often caught up with other materials floating around in a gap and remain stuck there instead of continuing to drift inward. They also tend to encounter pressure traps, or regions of increased pressure that cause them to accumulate, which does not completely prevent them from drifting but acts as a cosmic speed bump. While there was some cool water vapor detected in these disks, there was not the large amount of vapor at the snow line that the team was looking for. Observations of the compact disks were a breakthrough. The data Webb beamed back showed that, while there were spectra suggesting the presence of warmer water vapor emissions far inside the disk, there was also an excess of cold water vapor emissions just on the outside of the snow line. It is from here that the water vapor will travel to the inner parts of the disk. Pebble drift and trapping provide a fundamental natural process for a large-scale link between inner and outer disk regions that may explain the cool water excess revealed by MIRI in the compact disks analyzed in this work, the researchers said in a study recently published in the Astrophysical Journal Letters. So what happens from there? Eventually, drifting pebbles that lack ice will collide with each other until they begin to accrete into what might eventually become a planet. That hypothetical planet may later be supplied with water vapor, and billions of years from now, it could even become another Earth. Maybe analogs to our planet really are out there. They just might not have formed yet. In addition, a new search for dark matter has turned up empty-handed. But, in a silver lining, the effort provided important limits that will help future experiments narrow down the hunt for this elusive substance. Most astronomers believe that dark matter accounts for 85% of all mass in the universe, and that its existence would explain the apparent extra gravity detectable around galaxies and within huge galaxy clusters. However, so far, no one has been able to identify what dark matter is made of. Until recently, the front-runner suspect had been a breed of particle called a WIMP, which is a neat acronym for weakly interacting massive particles. These theoretical particles are thought to barely interact with normal matter except when it comes to gravity. However, the Large Hadron Collider, the world's largest and most powerful particle accelerator, has failed to turn up evidence for the existence of WIMPs. As Deepak Kaur, a professor of physics of the University of the Witwatersrand in Johannesburg, said in a statement, WIMPs is one class of particles that are hypothesized to explain dark matter as they do not absorb or emit light and don't interact strongly with other particles. However, as no evidence of WIMPs has been found so far, we realized that the search for dark matter needed a paradigm shift. Some alternative models of dark matter posit that, rather than being weakly interacting, dark matter could actually interact strongly with some particles in the Standard Model, which is a framework of particle physics that describes every known particle, as well as how each particle interacts with and relates to one another. Dark matter particles are believed to exist beyond the Standard Model's scope. The models that predict strongly interacting dark matter, rather, describe an entire menagerie of theoretical particles, starting with basic dark quarks and dark gluons. Those are like dark mirrors of quarks and gluons that are the fundamental building blocks of all visible matter and surely present in the Standard Model. Now, Kaur and his former student, Sukanya Sinha, who is now at the University of Manchester in the UK, have developed a new way of searching for these potential dark quarks and dark gluons in high-energy collisions between protons that take place within the Large Hadron Collider. When protons come together at almost the speed of light inside the Large Hadron Collider, they are smashed apart into their component quarks and gluons that swiftly decay to produce a shower of short-lived subatomic particles. These particle showers are referred to as jets. Kaur and Sinha's idea, which formed the basis of Sinha's PhD, is that possible dark quarks and dark gluons could decay to produce a mixture of particles, some ordinary and some dark as well. This would result in what they refer to as semi-visible jets. Jets are produced in pairs, they explain. And if one normal jet and one semi-visible jet were produced side by side, the dark particles would carry away some of the energy, leading to a telltale energy imbalance reading because the dark particles would not be seen. Carr and Sinha have led a search for these energy imbalances with the Large Hadron Collider's ATLAS experiment. Because a slight mismeasurement of two normal jets could mimic the energy imbalance of a semi-visible jet, however, the data from ATLAS had to be analyzed very carefully. The duo found no evidence for semi-visible jets, but that doesn't mean they don't exist. The ATLAS results, published in the journal Physics Letters B, point to upper limits for the properties of these theoretical dark particles, allowing future experiments searching for them to be fine-tuned. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.